the teams did a really great job putting together some nice presentations, and they're going to pause for questions at the end. So it's a good opportunity to ask questions. They did a lot of great research, really nice project. And, I think they'd welcome some. So first up, we're going to do the social distancing device with Stephen and Justin. You guys are going to present, yeah? Justin's going to present.
Yeah.
Take it away.
Can you show our PowerPoint?
Oh, yeah.
Am I not seeing it?
I haven't brought it up yet.
Okay. Justin, are you able to bring it up, or would you like Professor Braverman to?
Oh, no.
Okay. Thank you, everyone. Thank you, everyone, for attending. I was fortunate enough to work here with my partner, Justin Roxas, and I'm Stephen Holmza. And for our capstone project, our title is Social Distancing Devices. You can go on. So in order to choose our project, we had to go through what was called a concept process, in which Professor Braverman assigned some assignments last semester. There were 5 of them: skills matrix, project skills and knowledge description, problem statements, solution matrix, and then partner selection. So our skill matrix was stating which jobs we'd be interested in and given their description on the skills and knowledge needed to perform at the job. Moving on to our project skills and knowledge description, we had to go through and define and describes those certain skills and knowledge in order to complete a certain task. Next one was, in my opinion, was the most important part, was problem statements, in which we had to submit 5 or more problem statements that we can address for a project. The problem statements that we addressed should be able to draw on the skills we have identified or to be developed during the course of executing our project. Right after the problem statements was our solution matrix, in which we were able to present a solution matrix and important attributes for the selected problem. And for partner selection, I've known Justin for my 4 years here at Central. We've had a couple classes together. Luckily, we've had the same kind of problem statement, in which our problem statement for our project was normal social distancing protocols such as signs and stickers do not seem to work in a working environment. A technology implementation could help enforce social distancing. And Justin will take you through our development process.
So for our development process, we, after through the semesters, we had to go through a process from stakeholder requirements, performing requirements analysis, system level requirements, and from that forming subsystem requirements and architectural design. I want to go over some of what we did for first for stakeholder requirements. So for stakeholder requirements, the goal is to design a device that helps enforce social distancing protocols for the work environment and everyday use that is simple to use with a small compact design. Mission profile. The device should help decrease cases of COVID by helping enforce better social distancing with notifications to the user within whenever another user gets within 6 feet. It should be implemented in like a business or workplace environment. Some of the constraints from like a stakeholder level that we thought were really important were like, keep in mind or false detections, the device not connectivity, the range of the device, and the notification, a notification and clarity of the notification.
So next
So
was, I'll get it. So next was our system level requirements of what we want our system to do. So we have it. So our social distancing devices, or our SDD for short, shall enforce social distancing in the workplace. So when we go through tasks of what we specifically want our system to do, it's when two users get within 6 feet of one another after a certain amount of time has passed, 10 to 30 seconds. The reason for 10 to 30 seconds is possibly a good amount of time that you could possibly pass COVID-19 to one another. If it's just quickly under 10 seconds, the chances of that are slim. But once you're in for that amount of range, users will get a notification. We have to make sure that the devices are able to connect via Bluetooth. And when the SDD notifies and registers that two users are within 6 feet, the database records both users being in contact with one another. And then making sure that our devices are able to sense and track where other devices are located. Next slide.
For the subsystem requirements, I'm going to be focusing. Main part of the project was the Bluetooth capabilities of it. So the social distancing SSD uses Bluetooth technology to track the users in real time to help enforce 6 foot social distancing in the workplace, alerting them if they're within range of one another. The Bluetooth we're using is Bluetooth Low Energy. It's a low power wireless communication technology that's usually used for like short distance and enables smart devices to communicate to one another. It's best used, I said it's best used in proximity. The short distance works in our case because 6 feet, it's quick and fast, or like snappy, compared to other Bluetooth options on the market. It is accurate compared to it is accurate to other Bluetooth options in the market, which means fewer false detections. The Bluetooth connection allows seamless connectivity within the system once the Bluetooth device is connected. So, yeah.
So next I'll take you through our requirements analysis and traceability. Professor Braverman posted this for an Excel sheet for us to go through for both semesters, in which we found it was very good for us to go through and update it through the 2 semesters. Found ourselves actually updating it throughout, finding new information in the second semester. So to start it off, we start off with ID 100, which is our base of our project, which is we want a social distancing device shall enforce social distancing within the workplace. And then we broke it up into 3 different subsystems. 3 main subsystems, one being notification, which is our 101 parent, and it's when two users get within 6 feet of one another after a certain time has passed, the users will get a notification. It then leads us to our second subsystem, which is our 200 parent, is that the device shall be able to connect via Bluetooth, for example, underneath to go off. So from 200 to 201, this is just for example, we listed that the devices are able to communicate with each other within 6 to 10 feet, just the base for the main 200. Moving on to our third one, which is our database. That's a parent of 300. We want the social distancing device to notify and register that 2 users are within 6 feet, and then the database records both users being in contact with one another. You can move on.
So these are some diagrams about our system architecture, about the whole grand scheme of things. On the left, we have the two devices, and they are attached to the users, right? And those two Bluetooth devices are communicating through low power Bluetooth, and they have the ability to send notifications. So like in our case, it would be blinking lights if you were in 6 feet with one another, and if that does happen, the devices store that data to the database. And then on the right, shows it in another, like, I guess, a fashion as well, about how like information is relayed to one another.
So as I stated before in the RTT, this is our first subsystem, which is our notification subsystem. The purpose of the system, which I stated before, is whenever it's within 6 feet, they'll get a notification whenever they're within range. Before we updated this recently, but before for our notification, we did not know whether or not our project was going to consist of a haptics or vibration for the notification, either light or either sound. Considering the boards that we got, which is an NRF 52840 development kit through Nordic Semiconductor, we were able to just try and program our LED lights. So we would just use the lights in this scenario, and the circuit of the Nordic Semiconductor is listed there. And Justin will take you through our second subsystem.
So for our second subsystem, the Bluetooth capabilities, I'm gonna break it down into like different parts. So like the application, it contains user interface, application logic, and overall application architecture. Host defines the characteristics, the services, and profiles which allow the Bluetooth to discover and identify other devices. The generic access profile, how LED device access and communicate with one another. It does broadcaster and observe, advertises the packets, and observe, listens to packets, and decides to interact depending on our case. Generic attribute profile, how data is formatted and set. This is for the database side of things, like store data if available when sending a request to the database. Attribute protocols, the rules of devices when it should act and how and what its role is. So security protocols, only Bluetooth devices that relate to social distancing should have access to one another. So like other Bluetooth devices shouldn't be able to communicate to the SSDs. Then controller, the bottom layer, the physical layer, where you have link layer, scanning, advertising, standby, and physical layer, analog circuits that transmit and receive data over the radio waves. Some of the challenges we had with Bluetooth and notification, like I said, false detection if the two devices are within 6 feet, but there's something in between them, like a wall, protective barrier. We want to minimize that. So like in the example I put, if one user is above another user but on different floors, it detects them being 6 feet. We want to minimize that. We don't want that to happen. And then the timing. The time it takes to notify the user when they are within 6 feet of someone else. So, testing it just depends on like the work environment, I guess. So if it's like there's a lot of like traffic in the workplace, you want to like increase that time of that the users have to be in 6 feet within each other. And other challenge we had to deal with is we should have focused more on the Bluetooth capabilities of the device, because on the first half of the semester, personally for me, I spent a lot on the database, but towards the end, it was kind of hard to work on it because if you don't have the Bluetooth devices communicating through, our project kind of falls through.
So as Justin just stated, our third subsystem was our database. we got its key functions into a graph of that. We want the devices to go towards an app in the iPhone that the users would interact with. And then the data would sort of just go through the AWS Lambda and its function, and then go through the Amazon DynamoDB. Justin, you can move on to the challenges slide. And right here is, and Justin kind of pointed out with the Bluetooth challenges, we kind of had too little to no knowledge with cloud computing and databases, which led to a lot of research and a lot of time used on it. We definitely spent too much time trying to research about it with the amount of knowledge that we had. We did learn a lot, but due to timing, we were not able to finish this stage of our project, unfortunately. So we kind of just threw out the database, but we definitely did want to include it and present of what we wanted to do with it.
Because like,
move on. Oh, okay, go ahead.
Because I was gonna bring it up later. Side. Do you should I go first, or do you want to do your end
Yeah,
first?
you can do your two.
Oh, to the top left, we have a schematic of the Nordic board of all its functions. You know, NFR, USB slot, the antenna, the RF connector, all the batteries, all the components within the board itself, which you see on the bottom left. Bluetooth state diagram shows the different states that we want the device to act in. Oh, screen is frozen. Hello?
I can still hear you.
Still okay. Still frozen right now. Yeah, okay. It has the different modes. So unconnected, from the very top, it's in standby mode until you turn it on, and where it goes into inquire, and inquire where it's trying to search for other SSDs in the area. And then it goes into paging. From paging, it addresses, like, you know, establishes that there's a connection between the two. So they can now transmit and receive information in the active state. And from active state, we have different modes in low power, which is park, sniff, and hold.
So
You can go, Steven.
I'll explain our two flow diagrams that we created. In the middle, on the bottom, is our Bluetooth detection flow diagram, in which we have our two STDs with our two users. It goes off into a yes/no basis flow diagram. If the devices are within 6 feet of range, it checks for STD clarification, and which we mean by that is that when the devices are searching for something, we want to make sure that it's just not a random other Bluetooth device. We want to make sure that it's another STD. So how they can tell that is through addressing. They have a certain type of address that they can find. So if it's not, it will keep on searching for nearby social distancing devices. If yes, they will keep on searching for more than 10 seconds. If it's more than 10 seconds, that's when it goes into our notification phase, which is our LED, and then it will send the information to the database, which leads to the flow diagram on the right side, which is right where we left off, that it's able to detect within 6 feet. It leaves off information such as a timestamp of when the two users were in contact, and the social distancing devices IDs are sent. It then would be sent to our user interface, which is our iOS application that we stated, and then through the AWS Lambda, which is our microservices, and then to the data storing, which is our AWS DynamoDB. And when researching this would be a .csv file.
So this is our bill of materials and schematics. On the left, just description of the different footprints for our board, different like I guess limits and values. And then on the right is just another schematic about how the layout of the board is when connected to a source of power. And the pinouts for all the pins. But in our case, we didn't really mess around with it.
So I'll take you through our implementation details and tools. For our languages, our boards were able to function through C++ or C++. In our case, I believe we use C++. And then for development tools, it's brought into 3 different phases. The first one is our hardware, which I stated before is our NRF 52840 development kits. And then also we wanted to go through Amazon Web Services, website online, try and get some tutorials and stuff in order to make our database work, which would go through and possibly use our Xcode iOS applications. And then Justin has the more experience with Sega Embedded Studio, so he can go through that part.
So for Sega Embedded Studio, I had to use various other applications besides Sega. So A-Link was a thing, NRF5 SDK. Those were all the files built in. Access files for Sega, and NRF Go, which is a another extension Sega, as well as the NFR Toolbox, which is an iPhone app that allows us to interact with the board using our iPhone. So that was used in our research purposes as well. So for implementation results, the key points for our implementation was the Bluetooth connectivity. So having the devices connect and communicate through Bluetooth was an important part for us. The iOS app pairing. So since we wanted to work with like iOS device, we had to we wanted to figure out a way to do that, and through one of the examples I'll be showing later, we did get that down. And then having the devices go into different modes of operation. So the low-powered modes I was talking about earlier, when scanning for other devices, and like just to be more energy efficient with our device, was another important factor. Some of the challenges we had to deal with, though, when looking at the code, I have a lack of knowledge in C++, so combing through the code was a bit of a chore because I didn't know exactly how a lot of the functions were. And then also having this, like, I guess this also comes with a lack of knowledge from C++, having to start from the basics. So even with, like, not even just Sega with C++, but like AWS, we had to like start from the ground up and try to build fundamentals before we can start looking at like example codes or like example tutorials online, because I personally, for me, I had no experience with a lot of the stuff we learned we have researched for this project. So for our testing summary results, the SSD sends out an inquiry request and finds another SSD result, which we were thankfully successful in. Bluetooth capabilities can communicate over a range of 6 feet. Later on in the video, this shows this, but this was also confirmed that we were able to do this. Notification goes off during edge cases. So in our working model right now, we don't have it. So the two boards are sending information to one another, but the board is sending a notification to a iOS device, which kind of can solve the simulates, I guess, what we want to do. And I just having the ability to send the notification off and testing, like, see if it goes like, oh, will it send a notification off in like 7 or 8 feet, or like what's the range? We in my testing we kind of solved that. And then for the last two, notification goes off when it's positive. Couldn't really solve that because I don't have we weren't able to have the boards talk to one another. And the database we could not finish due to lack of time constraints.
Would you want to do the reflections now and then the video, or do you want to do the video now?
It's a good idea to do the video right now.
Okay.
Yeah. Second. My screen showing?
Yes.
Yep. Okay. So here I'm starting up the board, turning it on, initializing the code onto the board. We'll show right here. It's cut off. It's showing like, yeah, the download was successful to the board. I reboot the board just in case. The blinking LEDs indicate that it is good right now. So here I'm connecting the board to the phone through the NFR toolbox. Here it initialized, but for some reason, when I was recording, it didn't show the distance between the devices, which normally it does. It shows it in feet, which was really important in testing, but later on I'll show you that it can work within 6 feet, and when it goes out of 6 feet, it does not want to communicate. Here, like I'm walking away from the board, you can tell that the connection between the board and the iPhone, it's goes lower and decreases. That's simulating the notification that I was able to get working with the code. So it's just showing like the range again. That the connection goes lower quality the further you go away. Reference, that's like what, 20 feet where I just was, right? I was there. As we get closer to the thing, the connection reestablishes. That's what out the notification of the app. This was showing the edge cases of the device, so how it can communicate. From the tape measure, I measured out what this was like 13 feet. This is where like it's where what do you call it? Communication to the board. If I press the button, the notification won't go off. Won't be able to send a signal. So it's like the limit of the board. I click the or alarm won't go off in the iOS device. Right here, 6 feet. It's able to send alarm notification. This right here is just showing how you can disconnect the board and reconnect. Here's the button layout of the board. Right there, I pressed like the third button, and yeah, I was able to reconnect through the device again. And yeah. That is all. I did not mean to. I meant to cut this shorter at the end, but my phone movie maker is a bit scuffed. Alright. Let me swap back to the slides.
So for our reflections about our whole capstone project, I broke it off into roadblocks and good developments that we found along the way. Starting off with our roadblocks, it kind of leads from one point to another, and our main roadblock was we should have spent more quality time on the main objective of the project. So from our problem statement, you were able to tell that we were more focused on a Bluetooth notification process. We definitely thought it would have been a very cool idea to include the database. Unfortunately, due to timing, and it leads to our second point of that we would have liked our supplies for the project earlier than when we got them. When we got the boards, we realized that we really had to focus on that instead of other stuff. We had to get the boards working first before we were able to get the database to be linked with it, with the app and stuff. So then it led to... Go on.
Go ahead. My bad.
Okay. And then it led to, fortunately for us, we ordered 4 boards, so I got 2 and Justin got 2. Luckily, because I was not able to work on the boards. From working from my dorm, I was able to use a Microsoft dock that from my laptop I was able to display to different monitors, but the USB supports only a 1.0 USB, where the boards wanted a 2.0. The computer was able to detect a board being on, but was not able to program the code to the boards. So fortunately, luckily for Justin, he was able to do that side of the project. And then probably for every single.
I'll go over
Go
something
ahead.
real quick about the roadblock. For the second point, having the supplies earlier. If we had them earlier, I felt like I could have worked more on like fundamentals of like fully understanding the code. I felt like it was kind of rushed towards the end, where there was stuff like I understood but didn't know really how to implement to our project, so it kind of got cut short. That's why we couldn't really get the boards to communicate to one another. But yeah, go on, Steven.
So it could be for everyone is that it was definitely hard to work on a project like this remotely. Not having that experience of meeting with one another in a classroom or a lab, to be able to work on these boards hands-on, being able to help each other out, just being there. I just felt like helping each other in person is definitely better than trying to do it remotely, when sometimes it's hard to see what their screen is or what they're doing wrong and stuff like that. And then Justin will take you through our last two roadblocks.
Oh, since I had to work with the network semiconductors and all the coding, I found that the various examples they had through the Nordic Semiconductor website, they had a ton, but like how they laid out the instructions wasn't really helpful and only really a guideline. Like sometimes, like at the start, there was like certain files that would I found out that only certain files only worked with certain boards. And the version types for whatever code you open, it sometimes like it seems like it's gonna work, but it doesn't. So like in our case, we had to use the PCA 156E, and there was like two other options. There's a 156 and just a 156 like F, I'm pretty sure. So it was confusing to navigate through that. And many of the tutorials they had through the website didn't really use Segar, so I had to play around with that to understand how to fully use Segar and like how to run code, edit, stuff like that. Because they used Keeley MDK, which needed a lot more work for us because we had to kind of translate what they meant in Keeley to Segar.
So I know that we're just getting around 34 minutes here, so I'll try and wrap this up. I'll take you through the good developments, and then we'll both talk about our personal experience. So for good developments, we found more time to meet, considering everything was online. With me being in athletics and dealing with school, it was hard for me to sometimes meet, but with it being online, I was able to just go in my dorm and ping Justin, and we were able to work with each other more than what I thought we were going to meet. Confluence, we used Confluence for our documents, and it helped us organize our project better. All information was available to us for both semesters, so if we had something to update, we updated it. If we needed something to look back to, we looked back to. And then basically the rest of our good developments is we just learned more throughout this project. We researched hands-on topics that we've never really experienced with here at Central. We learned more about coding through Segar Embedded Studio. We learned more about sharing and uploading code through Bitbucket and GitHub. And we're able to get experience with project development cycle, like our stakeholder requirements and the different kind of requirements that we needed in order to start this project off. But going through my personal experience, I enjoyed doing this with Justin. I definitely felt like I was very inexperienced going into it, based off the knowledge that I obtained in the last couple years. It felt like I found myself researching a lot, but with the help of having Justin by my side, and Professor Braverman was always there for us to meet and stuff and explain things further, which was great. But just from my personal experience, the only thing I can think of is that I found myself having the lack of knowledge, and definitely a lot of things that I developed in the last 2 semesters doing this project.
Yeah, going off him, like for my experience, like I did learn a lot, especially with Sagar, and then earlier in the first semester, a lot of AWS, like how cloud computing works and how all the databases doing those tutorials through Xcode. There's a lot of troubleshooting there as well, where I had to like, since I think a lot of the Amazon like was doing a iOS application example, and I couldn't do it because apparently the application they use is a Mac only. So I had to use like Unity or something to run the code, and yeah, it was definitely an interesting experience because a lot of like researching, translating, like trial and error to get stuff working, and it just felt like really nice to get something at the end, something to work, you know. But yeah, it was definitely an experience, and like I said, the like what Steven said, getting experience with the project development cycle, I found that really useful and like really useful in the long run because that's like how would be in the workplace. Have anything to add, Steven?
No, this is where the end of our project is. We thank you for listening to us. I know we ran a little bit over 30 minutes, but we'll be taking any questions now. Take it easy on us, please.
Hey guys, I have a question for you real quick.
Jessica?
Yeah, first off, I thought your project was really cool. What were you guys? So I saw in the video you guys were using, it was attached to a cable. But
Yes.
to put it on a person, you would have to do like a personal device, like a battery or a power solution.
Yeah, like a battery. Yeah, just for like our testing purposes, this was powered through USB.
Okay.
Like if we actually continued to further this, like it's just concept. So if we like further on, like we would have done it like a rechargeable battery, kind of like like a watch or something.
Gotcha. I was
Yeah,
just
to add.
sorry, go.
No, I was just saying, just to add to that, Justin just hit it. Like the first semester, when we talk about our requirements, we actually put that down. What were we gonna do? Are we gonna use a pin that was attaching to maybe like a tie or something, or we're gonna use like a watch or something like that? We were looking into batteries for that, but for the testing purposes, the best way to get a Bluetooth low energy device was through Nordic Semiconductors, and we were able to order the boards and just test it through that way.
Gotcha. Cool. Yeah, because ours is also, something that would require a battery, and I was wondering if you guys had any research or solutions for that. It's cool. Rechargeable batteries.
Well, thank you for your question.
Great job, Steve.
Hello.
And great,
Oh,
really
hi,
great
John.
reflection. Sorry, go ahead.
Hello, can you hear me? Also, this is Dr. Wu. But
Yes, we can
I
hear
wonder
you.
if anyone. Excellent. So I also think your project is very, very interesting. And I was, when I see the title first, I was hoping, in the fall, I'm going to be in the classroom. Maybe I can try those. But I totally understand how many difficulties that you guys had in the past year. And I also found the two challenges you guys had. One is that you wish that you could have more on the cloud computing technologies, and also lacking of this C or C++ languages. So I think the faculty are also feeling the same urge that recently we have a new cloud computing technology courses proposed already.
I heard about
there
that.
will
I heard
be
about
more
that.
courses on that. Yeah.
Mhm.
Unfortunately, you guys graduated. Yeah.
The only one like offered right now is like a research class right now, right? Like intro to cloud computing.
Yes, special topic sometime. Yeah, but we proposed it. It has been passed by the university at the university level, and should be in place, very soon. And there would be following up more advanced cloud technology courses on. Another thing is the C++ problem. whole park raised this issue several times. He said that the CS 151, 152 should be C, C++, not the Java. So that's why a few faculty members like your Professor Braverman, Professor Kutzkos, and Dr. Park, they have got the suggestions for CS 151 and 152. We already to the computer science department, and hopefully they can adjust those two courses, maybe just for us to create C and C++ sections. So that should help, the future students. But I do feel your frustration on that, and I'm very happy that you learned a lot through that process. Yeah, and I think you guys gave those students who are in the CET 497 very good advice is to maybe like decide what your project is gonna need earlier, and once the semester starts for 498, get an action quickly on that, and if you need to contact the department for some support. We understand how our students have been, difficult by, doing work remotely. But overall, I think your project is very like having realistic meanings and interesting, and hopefully in the future more, convenience or supports that you're gonna receive. Good luck.
Thank you. Thank you.
Thank you. Okay. All right. How about next up? Bring up the AVR team.
All
Thank you,
right.
Justin. Thank you, Stephen.
No problem.
Good job, guys.
Yeah, excellent job.
Yeah, thank you guys.
Thank you.
Hello. We're gonna start with our demonstration first. So quick, what's the word I'm looking for? Quick primer before we go into the demonstration. This is we were working to build an autonomous vacuuming robot that would be able to go in a room and move around and be able to plan its own path and then do its own path and go back to its charging station. And for our demonstration, this is what we have. And please enjoy the video. Hi, this is going to be my part of the demonstration for building the autonomous vacuuming robot, or AVR. This is the fully built bot. As you can see, the LiDAR is spinning and sending data to the Jetson Nano. In my demonstration, I'll be focusing on the path plan for AVR. First, we're going to look at how AVR is going to be making the map. The bot is going to be using a combination of LiDAR and hectoslam to create the map of the area. As the LiDAR spins, it will send the distance and the angle that the laser travels before hitting an obstacle. As you can see here, this is the live feed of what the laser point is outputting to the bot. Then, using a pre-built algorithm called hectoslam, we're able to convert the data into a static image file or static map file. Hectoslam creates an occupancy grid in the form of a 2D matrix, with every point either being a 0 for no object, a 1 if there is an object, or a -1 if the space is unknown. As you can see here, these points are indicated by the color of the pixel. Now, looking at how to read the map, we first must process the data. We currently haven't finished the complete algorithm, but are in the middle of coding of it. Allow me to walk through the general concept of what we have. There are two most common path planning algorithms that is commonly taught. The first is called the Dreska algorithm, and the second is A-star. These algorithms are able to find a path between 2 points. Here I have an example of the Dreska algorithm performing its search from a starting point to the endpoint. The concept of the Dreska is from the starting point, it will look at each of the neighboring points that it is connected to. Then it will record the cost to travel to its neighbor. Through each iteration, AVR will travel to each point and see who are the neighbors at each point. Overall, we're going to be tracking who we visited, the cost distance to said neighbor, and we're going to be tracking the overall path. Moving on to A star, you can see that this one is going to be a little more focused. Instead of looking at each neighbor holistically, we're going to be trying to make an estimation to who is closest to the endpoint. From that, we're going to be able to do that, we're going to use a heuristic function that's able to give an estimated cost, an estimated distance to goal. Overall, we're going to be tracking the distance from start and the cumulative sum of the distance between each point using the heuristic functions. For our purpose, we're going to be using A star and placing waypoints for the bots to plan around. The bot is going to define the boundaries and obstacles using the map that we retrieved from Hexoscan. It's going to scan through the occupancy grid that AVR receives row by row. Applying some logic to be able to determine what are the points of interest. For example, after passing an obstacle point, and the rest of the row is going to be -1 or unknown, then it should be considered a boundary point. Afterwards, AVR is going to be looking at these two sets, the boundaries and the obstacle waypoints, and scan each row on the same horizontal plane, looking for some points. When it's able to find a point or connect, it will attempt to connect each other if there is no boundaries, using the A star algorithm. If it encounters an obstacle, then the bot will move up one vertical unit, the size of the bot's sweep range, and do the process in the opposite direction. This will create the zigzag that you see here. And this is going to be the path that the AVR is going to be moving towards.
Hello, this is Quentin Brooks with the test demo. The first one I want to show you is the Ultrasonic Sensors. This test shows the object distance detection and the stop-slow signals from the sensor. So you can see on the left are the sensors pointing to the wall, and it's reading about 90 centimeters, 90 to 96 centimeters to the wall. You can see that each sensor left, front, and right has its own range and continuously prints on the Arduino IDE serial port. And right here you can see slow left at about 30 to 20 centimeter range. It'll print out slow signals. And it's off camera right now, but you can see as I move my box closer to the sensor, now you can see the stop signal. So, and you can see it's from the left. So each sensor has its own stop and slow signals. So in this test, the ultrasonic sensors are the stop and slow signals are being broadcasted to the cross topic chatter. So in this test, you won't see the front, left, and right distance, but just the stop or slow. As you can see, I put an OK. So OK just means that the sensor is not picking up any signals, like stop or slow signals, so it just prints out an OK. So without it, I noticed if there wasn't any chatter, same test, but with dual motor speeds. But one is going forward direction and one is going backwards. So you can see the left one here, it's going to spin down, which would be backwards, and the right would go front for forward. And they go through the same cycle speed between ranges 20 to 250. And the last test is the wheel motor's keyboard input. So I used keyboard inputs A, S, and D to represent if a sensor signal was detected. So if I pressed A on the keyboard, it would go through a cycle where yeah. So you can see here, the left sensor move right, it will initiate a script that will move backwards and move away from the left. So essentially turning back and moving towards the right. And then once that is executed, it continues moving straight. So all it does is cycle through, so essentially what I was going for with this one is to continuously just move straight, and if A, S, or D was typed, it would just go through a cycle to move away from that object. So S represents just moving backwards. Then the right sensor detected, it'll move to the left.
So that was our demonstration. I hope you can keep that in mind as we describe our implementation process and how we were able to come up with what we actually made, or how we wanted to start from. So as mentioned before, my name is Javier Diaz. My partner is Quentin Brooks, and this is our mobile robot. When we originally started the class, we were asked to look at what type of jobs that we wanted in the future. I personally wanted to get into hardware engineering and dealing with sensors. I thought it was always something very interesting to be able to read the data from the outside world and then analyze it to be able to make a reaction to it.
In my career matrix, I wanted to try to look into some professions I was interested in, like electrical, computer, and IT system engineering. So what I wanted to go for was something that would require design, development, testing, implementation into projects.
And in the beginning, Quentin and I actually had two different projects. Originally, I started with the autonomous vacuuming robot. He started with the autonomous warehouse robots, which would go around the warehouse and be able to move through there. At the end of the first semester, we decided that it would be better if both of us collaborated on one project together. We ended up going with the AVR. And for the final concept, we just concentrated on the robot's ability to map and actually move around a room without hitting anything and independently. Oops.
So for the development process, a few main requirements. We went through the system requirements. What we wanted to come up with was what our project really needed was a system to vacuum, a system to map and travel around the room independently. It needed to detect and avoid any objects or any ledges, and to be operated on a battery. From there, we went to subsystems, taking our system requirements and going lower with them, figuring out exactly, what the navigation needs, how it moves in a space independently, how the objects avoid, what programs will need, or or any interrupts to avoid, how the systems will interact with each other as well. So when we figured out what our subsystems were, we looked into system specifications. So breaking down the system, we have we wanted to understand the hardware, software, and interfaces for each system to work and how that works, and finalizing exactly what the components need, the computer language software we need, any operating system for each subsystem to communicate with, and that brought us to our implementation, how exactly these will work together, and coming up with some test cases and what environments we want to work on. And with testing is actually executing the testing, kind of testing, excuse me, testing our theories of our implementations, seeing what works and what didn't work.
For our requirements, we decided that the 6 most important requirements for this bot will be that it must be able to vacuum, it must be able to travel around a closed independent area or closed area independently, meaning that like if it's in a room, travel around the room. It must be able to make the map of the room. It must have a ledge detection, meaning that it won't fall off the stairs if it somehow encounters a hallway with the stairs. It must be able to avoid objects, so it's not just running into them and just staying run into them. And it must be battery operated, so it's not tethered to a wire that it has to bring around the room, possibly tripping or even tangling itself up with other objects. So this is our system architecture. We are originally going to have a central computer that we're labeling AVR, and then all the other modules are going to be talking to the central computer and then making decisions, and the central computer will make decisions on how to proceed from there. We have a navigation system, a vacuuming, an object detection, and a ledge detection, as well as a charging station that will connect to the AVR and a user interface, as well as the debris container that will hold everything, and AVR will figure out when it's full and be able to actually let the user know what to do. Quentin?
I'm sorry, I was muted. Okay, so the array proximity sensors, if you saw from our test, we had the front, left, and right sensors looking straight. This would bring to our object detection processing, which would be like the Arduino IDE that we had, which will eventually affect the AVR motor drive. So depending on what signal the sensors gave off, it would affect what direction the motor will turn. That's it.
Okay, cool. For the subsystem, so this is going to be our navigation system. So we're going to get the location change data. So that's going to come in the form of either encoders from the wheels or the IMU. So you're going to get the how far did it move from the beginning, as well as the distance measuring sensors. So we're going to be measuring where are the walls, where are the objects in respect to the AVR. And then using that data, we're going to build the map and we're going to do the localization. In our instance, we're actually going to be doing them at the same time, called SLAM. And then using that information, we're going to create the path for the device, and that's going to tell the motors how should it move from there.
Now, this is a subsystem for the vacuum that we eventually did not go forward with due to time constraints, but what we had for this was a vacuuming processor, a motor head, a suction tube that would be attached to the debris container, and then that would go to a sensor. to detect if the container was full, to send a signal to the user for any errors, or to notify the user to empty the robot. And we also had an implementation for suction power, so you could, whether if it was like carpet or hardwood floor, the suction power will adjust to that surface it's vacuuming.
For our ledge detection center or ledge detection module, we actually just had a density sensor, so this can come in the form of ultrasonic sensors or IR sensors, since it's going to be a relatively short distance that it needs to measure from the bot to the floor versus the bot to a ledge, like staircase. And then once the sensors detect that it's past the minimum distance, then it will tell the motor drives to stop. So now we're going to go into our design and models.
This is the implementation trees and tools, or tools and details and tools tree that we have. For development tools for hardware, we have a Jetson Nano, a Arduino Uno, a LiDAR, an IMU, and we used ultrasonic sensors. And for software environments, we used Arduino IDE, Linux operating system that was on the Jetson Nano, and the ROS robot operating system. And with ROS, we had for navigation Hector Slam, and for map generation and navigation Hector Slam, the RP LiDAR, ROS Serial, and Navigation Core. And for languages, Arduino, which I think we came to a conclusion was like a user-friendly version of C++ or Python. Arduino IDE is very user-friendly, so it has a pretty convenient way to download libraries and tutorials on how to use their software. Along with Python, that was a pretty easy language to use for like our ROS environment, and we used MATLAB.
Python is the best language, and so is MATLAB. Yeah, so Arduino is a simplified C++, and it has nice libraries that we're able to use that's able to obfuscate a lot of complicated code. So for our interface diagram, so this is going to be our interface diagram. This is how everything is going to be connected. The Jetson Nano is going to be the central that you can see here. It's going to be connected to the motor drive through I2C and the IMU through I2C, and it will be able to connect to the Arduino. So the Arduino is offloading the real-time processing of the ultrasonic sensors and then uploading to the Jetson Nano when an interrupt flag is sent, and actually tell the bot to either slow down or to stop completely. The LiDAR will be connected to the USB, or the LiDAR will be connected through USB, and the battery pack will actually connect to both the motor driver, Jetson Nano, which will power everything else.
Now this is the wiring diagram of the whole system. So starting from the left, top right, there's the Jetson Nano, the big square. We had a storage space of 125 gigabytes, Wi-Fi capabilities, and we have a power supply connected to that and the motor drive. For the GPIO pins, we used, just to clarify, we did have two robots. So our main robot didn't have the breakout board here that you see off to the left or off to the right of the GPIO pins, but the SparkFun Quick ecosystem was convenient to attach the IMU and the motor drive through I2C pretty conveniently. So that's what we had with the IMU and the motor drive. The motors were attached to the motor drive with the LiDAR connected through USB to the Jetson. And the sensor system was independently operated with the Arduino and coded through the Jetson Nano Arduino IDE software. With this, we just had 3 ultrasonic sensors connected to its own GPIO pins, and through ROS serial, was able to print that through USB to the Jetson Nano.
So, we wanted everything to be powered through battery packs, so we obviously needed to figure out what type of batteries should we be using. The Jetson Nano and overall the bot in general is a power-hungry device. The Jetson Nano requires 5 volts and a minimum of 2 amps. If it goes below 2 amps, it will just shut down. The LiDAR also required a minimum of 4.9. It can go up to 5.5. It actually has a separate power. It allows you to actually power the motor that spins the Jetson Nano or spins the LiDAR to be separate, so that way that the power connections are separate and you don't get as much noise as you would. That has a current draw of 1 amp, and then once it's starting, it's 1 amp and then drops down to 600 milliamps. To quicken IMU breakout or just powered at 3.3 volts generally, especially since the GPIO pins from the Arduino and from the Jetson Nano is going to output 3.3. It has a pretty minuscule current draw. The motor drive has a maximum of 11 volts, and when it's connected to and it has a signal from the quick to be 3.3 volts. The wheels are going to have a 3 volts to 6 volts with a continuous no load current at 150. So once you actually have the bot running with all the weight that it has, it should go up. The Arduino Uno, it has a minimum of 550 milliamps, and the Ultrasonic Sensors for 15. Overall, we have 10,000 milliamp hour battery, so we expect to get about an hour to 2 hours worth of moving around with the bot. Personally, when I had the bot running on my own end, when I had the LiDAR attached, I was able to have it running for about 4 hours before it even dropped below 30%, the battery. So it's pretty good at running.
And the pinouts, this would be the pinouts for Javier's version without the quick I2C ecosystem. So the motor drive would have connected through I2C on pins 3 and 5 on the Jetson. The LiDAR and Arduino would be connected USB. The IMU also would be connected I2C to pins 27 and 28. And on the Arduino, GPIO pins for the sensors, left, front, and right, would be connected through pulse on triggers pin 3, 7, and 4, and echo pins 2, 8, and 5.
So for our implementation results, we were able to get the A-star path planning started up and starting to operate. We were able to get an ultrasonic sensor function working. So as you saw in the demonstration video, we're able to see the wheel motor function. We're able to build the physical bot. As you can see, the picture next to it is actually the bot itself. Unfortunately, the top of it got cut off, but you can actually see how the ultrasonic sensors should be oriented and how it would be in the front of the bot, and then the LiDAR will just sit on top. We use ROS as the main decision making, as it's very nice for making a lot of peripherals talk to each other and be, as you saw, being able to read from the Arduino and actually being able to upload. Some of the challenges though that we had was the ROS hardware integration, meaning that like getting ROS to read the hardware and actually interact with it took some finagling. On my own personal end, my motor drive just wasn't working. I had tested all the motors. They worked fine. I had tested the Jetson Nano. It is outputting I2C correctly. We are able to read from the Arduino, and we're able to read from the motor drive and get the correct address that we were looking for. But for some reason, it just didn't work. So that kind of put a big damper on what I could do. It took out 3 weeks. It took me out for about a month trying to figure out why the motors just weren't working. And Quincy and I both had the experience that understanding how ROS nodes communicated to each other just had a layer of it required a little bit more than what we knew. but Quentin had some success with it. I was able to get success with it through accessing the map server to actually access the map that Hector Slam created and seeing that file. Kind of, but there's still a lot more to investigate in.
Yeah, it was a lot of. I would say it's a lot of troubleshooting because, on the test video, I was able to get maybe like one node to work, which was already part of the ROS serial library, which was just reading the serial information from the Arduino and printed on the chatter topic. That worked, but when I was trying to, implement off the book, create my own node for the motor drive and getting those like keyboard inputs I had for the test to work with the chatter, due to time constraints that I couldn't get that node to fully function. So I would say like troubleshooting time took a lot of time, and for like researching more on ROS.
Yeah. No, I agree. Overall, we'll talk more about it in the reflection, but yeah.
For
In
the
terms of
tests,
test results.
for the tests, I would say the test to the ultrasonic sensors worked. I wanted to test setting up the one sensor independently, and then I wanted to test up 3 together, and then I wanted to test the stop and slow sensors or stop and slow signals. So I would say the sensor part was a success. I was able to get that to operate the way I wanted it to. You can do test 2.
Yeah, and then test 2 was to actually use the LiDAR and move the bot around so you can get the map. And what does the map look like at the end? So the end result of the test was have a map that's accessible to the user and be able to look at it.
I should have switched test 3 and 4, but the wheel function, I would say, independently without ROS worked. I was able to script through Python some wheel movements to turn it left, right, or backwards. So I would say that was also a success. Test 3, object detection, I would say half success, because I was able to simulate through the keyboard, if statements with the keyboard. If I pressed A, it would stop, turn left, B, or S or D for any other direction. But getting it to work on ROS and actually, building the robot and letting it run independently, due to the time constraints, I couldn't get that to work. So I would say that was kind of a fail, but worked in simulation.
The final test was path planning, and that was going to be what you saw in the demonstration. You saw a very simplified version of it because obviously you want to create the zigzag pattern and you need to be able to place the waypoints for a star to actually path or be able to find the paths that it should be doing. I was able to get a little bit of it, as you saw in the video, is which I was able to succeed. I enrolled in a class, and that was one of the homework assignments for it. And moving on to the next portion of this thing would be actually planning or programming the waypoints and dealing with the map and actually being able to put the points down. We do have other tests that we didn't get to go to. So for instance, we wanted to be able to test the IMU and see what type of data we're getting from the IMU and how we can use it alongside with the LiDAR. We also wanted to be able to indicate that the LiDAR has finished, or that AVR has finished the map of the room and will be able to, is going into the path planning mode. So that would have been indicated by the LiDAR to stop spinning and it to just stop and standing still. So overall, so moving on to our reflections, overall I thought we did a great job with the constraints that we had. Working over online had its own technical interests, but I felt like the level of inexperience really prevented an efficient way to research. So for example, I was learning about how to read sensor data, and that brought me into Kalman filters, and that was a very interesting read. It took me a month to read it, only to realize that the LiDAR actually already has its own it has its own laser filtering system, which is why it's able to output such a nice map that you saw in the demonstration of the live feed. And so a lot of things like that where I just didn't know what I needed to know to be able to research effectively. Like, for instance, knowing about path planning and the different terminology. So for getting that zigzag pattern, it's called coverage planning, which sounds obvious, but those keywords are not going to generally be mentioned because a lot of times you want to get from point A to point B. You're not really you're not trying to cover in a whole entire area. But I was able to find a class that was actually taught computational path planning, and it's been very interesting to look at. Overall, just like mentioned, if I knew a little bit more, I could have done more. But what I learned was so interesting and fascinating. It helped solidify my goal to to go into electrical engineering, go into hardware engineering, and do more with that.
And for me, looking back, I think it was a little counterintuitive to start semester one with two different ideas. They were similar on paper. You know, we both had plans on, like, okay, both our projects will have motor drives and sensors and mapping and localization. So in theory, we were going to bounce ideas and do it that way. But in hindsight, it probably would have been more efficient if we were to just hone in and focus on one project in the first semester and really ironed out more detail in the first semester, which would have extended our time for development, which we had a lot of time constraints at the end. But I think our development and implementation were pretty good, and I was proud of what we did, and at least proud of what physical tests we got done. So overall, I think we both learned a lot, and it definitely gives me something to think about when looking for like a profession.
So let's open up the floor to y'all. Do y'all have any questions for us?
Yeah, I have a question. You said, it's Peter Katsoukas here. You said you ditched the idea of doing the vacuum. When did you make that decision, and how did you make that decision?
So we didn't mean to ditch the idea of the vacuum. We still want the vacuum, no questions about it. However, we found that it was more interesting to learn the path planning and the autonomy of it all than it was to just send a relay switch to a suction head, and then it will start spitting up and spit it to a debris container.
Yeah, and like we said, we had some, like, I would say this was a Javier's idea for semester one. So me hopping in, we had so many we had so many great ideas of what we wanted to do. I think the problem was there were so many implementations that we had, but with the time, when it came down to actually ordering the parts, or there was a lot of stuff we still had to. There was more research to do, and not so much time. We really had to think about what parts to buy from the school. So we decided, just focusing on the navigation, the object detection, and localization would have been better to concentrate on something, as opposed to having less of a project finished, something more concentrated.
Okay, thank you. No, I'm just I asked the question because of the 497 students on the call, and just getting them to think about the the subsystems of their projects and what they can prioritize in terms of getting something done for the end. Yeah, thank you.
Thanks for the question. Anyone else?
Javier,
Hi.
as I have this question, I remember seeing the testing that you showed at the beginning. What tools and how does this robot and the data then, so do you have a pre-made map, or how is this map is being made on the real time, or did you collect the data then transfer it somewhere, then somehow make the map available?
Yeah, that's a great question. So actually, so the bot is going to be making the map real time. It's going to be using so ROS has a node, or has, the way ROS works is that it's going to be using, it is running a central core, they call it ROS core, and you're going to be adding packages. Within the packages, there's one called Hector Slam, and Hector Slam is actually going to read the data that we're getting from the laser point, from the LiDAR, and from the IMU, and be able to create the map that it has around it currently, and it will be able to localize itself within the map, so we can actually determine how far the bot needs to go before hitting an object, or before it needs to make any changes. So this will be happening live, real time, and the path planning would be done live in real time as well. That's why when I mentioned in the demonstration video, we're going to be going around the room, then we're going to determine what are the boundary points and what are the obstacles, so that way we can actually connect each of them and be able to make the path. For testing purposes, you can get a predefined map, which is probably going to be nicer because a room will never be as nice as a square map that you find online. But yeah.
Excellent. Thank you.
Anything else?
Great job, Gwen and Avi.
Awesome. Thank you very much for listening. Hope you all have a nice day.
Okay, next up, room reservation system. Brandon and Mohammed, please.
All right. Do you mind showing the video?
Want me to show the video first? Yep, you got it.
Yeah. There's no sound.
There's no sound.
Yeah, you may want to stream the actual thing itself. Go.
I could actually stream it, Braverman.
Okay.
Alright, so this is our presentation on our room reservation system. Again, my name is Brandon Shin.
My name's Mohammed Udrouch.
And to start off, we have our problem statement listed here, and we're going to talk about how we were able to derive this statement based off of the previous processes mentioned, such as the solution matrix and the skills matrices we did in the beginning of 497. So our problem statement was a college or student union needs an innovative and friendly way to reserve rooms to students and organizations. And the second part of it was that the system must also send out a confirmation to the clients or the students that reserve the space. So we were able to derive this problem statement by listing using a skills matrix and solution matrices to figure out based on job positions like computer engineering, software engineer, hardware engineer, or system administrator, manager. Our project focused mainly on the software engineering side of things because it is all software.
One of the first steps that we had to do was identify who would be interested in our system, and those people would include students, clubs and organizations, professors, staff, maybe the president, even some outside clients. And we also defined the requirements based on the stakeholder needs. And a couple of examples would be the capacity of meeting needs to be recorded when booking rooms. The system should include days and times where the rooms are closed, and the system should be mid to low cost. And the next step after that, we made user cases, which is what users would go through when reserving a room. And we have an example of it on the slide. And the case would be the steps taken to reserve a room if the user already has an account created. And these examples help us envision the different elements of the system by imagining the process of reserving a room. And the software requirements listed at the bottom are just general product functions like storing user inputted data, applying collected data to filter out an outputted selection, and prompting users to enter data to collect that important information.
This slide is a few examples of our requirements and traceabilities throughout the process of designing this project. So based off of the stakeholder requirements on the left, we were able to come up with a few key functions on the right. So the first stakeholder requirement of the capacity of a meeting needs to be recorded when reserving the rooms. The functions that fulfill this stakeholder requirement are on the right. And these are: the system shall require that the maximum capacity is entered before confirming a reservation, and that the system will only show clients rooms that can fit the entered capacity. Another stakeholder requirement that we had was that the system includes days and times when the building would be closed, and this directly relates to the system allowing the user to be able to select a date through the web page. Our mid to low cost requirement from the stakeholders will be shown later that based on what system elements we used, and they'll be low cost. So for our system architecture, the left diagram is the main architecture of the system. This was one of our first diagrams of being able to kind of envision what each element of the system was going to be. So ignoring what's in the parentheses, these were just elements that were there as placeholders. We saw that the system was going to require a user interface, and through this interface, it was going to authenticate the user into the system and allow access to the application. The data stored or the data received from the user by the application was going to be sent to the database, which would be accessed by the authentication tool in order to also authenticate the user. We were going to have this database also save contact information and send it through an emailing tool back to the user once they had confirmed a room.
And on the right is basically our early state diagram of the steps a user would take when interacting with our system. So they would enter the web page. If they would want to cancel a meeting, they enter their reservation number and it would send them to a cancellation page. But if they wanted to reserve a room, they would fill in the information. That information would be sent to the database. And originally we wanted our system to send back only like the rooms that are available, but we didn't end up going that route. And we were also supposed to have a confirmation page.
Moving on to our design and models. This one is you.
Okay. This is a state diagram of authentication. So, a user creating an account or just signing in. So, if they are registered, they would enter the login credentials, and the authentication tool that we use would identify the user and authenticate them and send them into our webpage. If not, they would have to register, entering their registration information. An email gets sent to their email, and they have to put in a code to register.
Yeah, so this was one of our subsystem diagrams.
And this is our database schema. Originally, we had 3 tables: users, reservations, and rooms, but now we only have the reservations and rooms. And the rooms contain the room number and the capacity of people that it can hold. The reservations table had included the reservation number. Where it says full name was originally supposed to be user ID from the users table. But since we don't have a users table, we just put full name instead. The room ID, date, time, capacity, and duration of the meeting.
For our implementation details and tools, listed here are different system elements that were seen in the system architecture before. During this step, we actually identified what we were going to build the system out of. So our development environment we used was AWS Amplify. The language that we wrote in was JavaScript and HTML. The database that we used was DynamoDB. We used IAM for the authentication service, and Visual Studio Code and React application to launch the app. All of these elements were pretty simple to integrate into each other because most of them were by AWS and were able to be added through the VS Code CLI terminal. The results we got, we were able to successfully take the data and store reservations into the database, as you saw in the demonstration. We wanted to be able to add the ability to cancel meetings for the user. But we weren't able to display the information back to the user, so they weren't able to cancel what they couldn't see. We created a function to filter rooms based on capacity, but we weren't able to incorporate it. That also has to do with the picture or the map that we tried to display during the demonstration. We were gonna have that map filtered out certain rooms based on capacity. Our first test cases were unsuccessful, again, due to mainly that picture and the map not being able to filter out the rooms based on capacity. Our first test case was that when a room capacity is entered into the system, the interface will again output the map and display the different rooms able to be selected, which was unsuccessful. Test case 2 was that when the user enters a max capacity, that the system will filter and display the selection of rooms based on that capacity.
Another test case that we had was when a user enters info to reserve a room, then the data shall be written into the database to make a reservation. That was successful. We were able to convert the data that was inputted into the data table. Our fourth test case was when a user enters info to reserve a room and that reservation is not available, then a message shall pop up notifying the user that the time and date and like all the information that they selected was not available, and that was unsuccessful. We couldn't get an error message to pop up when there were identical reservations made. And we also included the codes that did work, even though they weren't implemented into the application. And the first one was the read function, and this just read or brought back data based off of whatever full name that was entered. The next one was the write function, which is the one that we actually did implement into our app. This takes information from the form, whatever the user inputted, and writes it into our reservations data table. This is our delete function, which deletes a reservation based off of the reservation ID.
Going on to reflections, designing the system was a bit more of a hassle than first anticipated. We wanted to use AWS and the services they provided to create a system based off of the elements that were already compatible with each other instead of trying to find elements online and trying to make it work. Mohammed and I were both inexperienced in JavaScript and coding in general, so going on with the system and what we outputted, I'm actually pretty happy about. So even though we weren't able to include a couple of the key functions, yeah, the mailing and confirmation service would have been definitely nice to include, but due to the lack of time we had, we weren't able to put that in. And we would have also used Python to create the code for AWS if we were aware of it before picking Java code or JavaScript. I mean.
And on my side, originally we were planning on using AWS, what was it? Or API Gateway and AWS Lambda. But after like 2 or 3 weeks of researching them, we decided to just move on without them by just using our IAM user provided by AWS. And it was frustrating, but it did kind of feel good and fun at the end when things did work.
Yeah, and just to end on a good note, I enjoyed using these new tools like Confluence and Bitbucket, which I never used before. They made collaborating online with Mohammed and getting feedback from Braverman very easy. I enjoyed that part of it. Okay, are there any questions?
So you're using a lot of AWS tools there. Have you looked at deploying it on AWS, or is that you're currently only running it locally on your machine? I think, yeah.
Yeah.
So I suppose the question is, what would it take to get it onto I don't know, Elastic Beanstalk or an EC2 instance or something like that in AWS?
I don't think we look too much into that. We're focused more on the functionality of it.
Yeah, and I think because we didn't use the API gateway in Lambda, it would be a lot harder to actually make it available online.
Mm-hmm.
But
Just
your
because we didn't.
backend, as your backend is live, right? That really was the database in the cloud, right?
Yes.
But your front end going with Node.js, yeah.
Yep. No, it should be, given that everything else is in AWS, it should be a relatively small step to actually get it fully live. But yeah. Okay. Thank you.
Thank you.
Good job, guys. And just like the previous two groups and the upcoming groups, all the challenges were really great learning opportunities. Even the stuff that didn't work that you researched, you heard it from all these groups. They learned so much about what it would take to get this done. So I applaud the fearlessness that most of you dive into something totally new and go for it. A great character, great. Any last questions for room reservation system team? Okay, great job, you too. Next up is emotion detector, Abraham and Anthony. And I think you want me to play your video. Do you want me to do that first, or do you want to do your presentation first, your PowerPoint?
Yes, play it first.
Okay.
Yeah, we'll play our video first.
Okay. I think I know what I did wrong last time. Give me 1 second.
Don't worry, I can just share it. All right.
Hello, my name is Abraham Agile.
And I'm Anthony Tran.
We have an emotional detector that presents the program that we're using, Anaconda Navigator, which is an environment of the program. The IDE that we're using is called Spider. This is where we did the implementation of our emotional detector. So this is a library where it has different apps where you can implement, for example, like Jupyter Lab, Notebook, etc. So we use Spider. Here we have a list of libraries that you can use to install. So for example, we use OpenCV, Keras, Pandas, and more. I'm pretty sure we'll go into more detail with that workflow.
So here we're just accessing the directory where the file is located, and we're just going to open it up in Spider. So it will take a few minutes. Well, not a few minutes, like a few seconds.
Here we have an overview of the train database file, which is a file where it has already database has already trained. So the purpose of this file is to read this file and sort it into numpy array in order to create measurements, also as well as recalculate and to sum it up, also to give an output of created file.
So by running this file, you'll see it comes over here in the console. The console is right here. This is the kernel of which this code gets outputted and read and understood by this kernel and produces what we need it to do. So by seeing this CUDA art, that means that it is using our GPU, and all this line says that is the TensorFlow device has detected my GPU and it's detected that it's CUDA enabled. So it is used as a sort of additional buffer, an additional tool to help perform the epochs with. And some of these are just simple, normal, like random, simple codes that we can just safely ignore. And over here, you see that the epochs are being done. And you can see the accuracy rising up based on each epoch. So we usually wait, so we have to wait for this whole thing to be done. But generally speaking, it only takes about roughly 10 seconds or even lower based on how good the network is of reading the emotions. We won't have to stay here for too long.
Do you guys want to jump ahead?
Approaching the halfway mark. You want? I can jump it.
Yeah.
More. It should be. There we go. So we're just gonna quickly go over in here, and we're gonna run this file here. Sorry about that. Like I said, it's running through the GPU, and as you can see,
The results. If you're mad, angry, neutral, whatever you're feeling, this is the result. Here's our emotional detector.
and then if I want to close out of this, I hit the Q button, and then we go into the folder, and it actually saves a picture. Now, because the accuracy is 0.67, even though it's smiling here, it produces a neutral, but as you can see, it works just fine. Thank you for coming out and watching this all the way to the end. My name is Anthony Tran.
And I'm Avery Hatcho.
And this is our motion detector. Have a good night. Okay, so that is the video, and then I'll just put up the presentation. the wrong thing? Yeah, it's the wrong thing. Share the whole screen. Okay. Hello, everyone. This is our emotion detector. I'm Anthony Tran.
Abraham Adjo once again.
All right. And then Abraham, if you want to start us off.
Yes, sir. So the concept process was beginning with basically from 497, finding potential careers that we would be interested in. Also finding certain skills, well, analyzing our skills and interests that we would like to apply related to our projects. While we analyzed, we had to do some research based off our skills, as I said, find some careers, find some potential projects that we would like to do. And once we did that, we came to a mutual agreement of the project of what we would like to do. And finally, we had to draw it up and plan up the project. So the development process was basically creating a proposal of the project of what we would like to do. So we wanted to do an emotional detector, so we had to break it down like basically give a proposal of what we wanted to do with the emotional detector. We created a stakeholder requirements for what we like for the emotional detector to have based off of stakeholders such as like exterior places such as schools, police station, other things. We had to design a architecture of it we would like to do and show a diagram or a drawing out of what the project is supposed to be. And in this class, we had to design a notebook, basically writing like a journal of we would like, also what we have researched. And finally, had to do the hands-on experience.
So for the requirements that we wanted to set up based on the stakeholder requirements, we decided that the camera must identify at least one person, which means that if it can't identify at least one person, then the entire project is doomed to failure. The camera must be able to send the data to the program, which means that the program itself must be able to read what is being produced from the camera in order to provide the emotional calculation. And it must be able to identify and classify emotions accurately. So what I mean by this is that it's able to determine based on what is being produced from the camera that is a neutral face, and within its own code, it classifies it as, hey, this is a neutral face, so we should display it as such. And then the last requirement, which we were unable to really replicate, is we must be able to save this to a database securely. So like we would have to, from the picture that we saved to our directory, that should have been moved to a database, but we didn't have time to do that.
So basically, the whole process of the system was to have a webcam process feature extractions, but also a database that will process the feature extractions where it will all link up by the emotional results. So basically, if you're happy, sad, angry, neutral, that's basically like the whole system of the program.
So from the subsystem architecture, basically we first have to train our system to be able to read emotions. And realistically speaking, there was no real way for it to accurately read emotional states. So what we did was we actually made it so that way it would predict an emotion based on the current image being passed into our program. And the way we would need to train it is by looking for a CSV file, which stands for comma separated value Excel file. And within the Excel file, there's three attributes. There's the emotion, which is labeled on a 0 to 6 basis, so there's 7 elements. The pixels themselves, which range from 0 to 255, and the sort of usage, so what it's going to be used for. So most of it was used for training, and some of it was used for the public testing arrays for populating the prediction model. So once we do that, we sort it into the array that we can access through NumPy. So NumPy arrays allows us to perform array manipulation and modifications. So without NumPy, this whole project, it is one of the key components for our whole project. So once we make the array, we create the parameters for training, such as the epochs, the number of labels that we want to separate them by, which is 7. There's 7 labels because of 0 through 6. And then we create the probability array using the mean and standard deviation, which involves some math. And basically, we normalize the array between 0 and 1 because the image that the CSV file produce is only a gray image. It's not a full color image. And we'll get into that more once we talk about the subsystem architecture. So then we create the neural network and we test it. We run it through the model.fit, which tests the whole network. And then we save the output and the weight of those outputs to the file to be used in this next part. So the next part is a bit more hands-on, or it's a bit more complicated. Basically, we read in the JSON and the H5 file from what we created earlier. We load the OpenCV, which allows us to access our webcam, and it gives us access to imagery and video library and functions. We record a frame from our webcam, and then we convert it to grayscale. So the reason why we do this is because it is much easier to create a accurate prediction when everything is one color and the RGB system is equal in intensity. So because they're all equal, the only thing we need to worry about is how light or how dark it is, which is very easy to think of as a scale between 0 to 1. And then we pass it through the cascade filter, which is a built-in filter that was created in that is loaded in OpenCV. Basically, it allows us to detect objects through the camera, and this filter was already trained to read in to recognize faces. So we simply utilize the cascade filter to help us recognize faces, because the only way for us to read emotions is through the face. And then we create the rectangle, and then we find the regions of interest, which is going to be the facial region. And then we load it as an array, and then we divide by 255 to emulate what we did in the training. And then using the trained model, we perform the prediction on what the emotion of the frame would be. And then once we do that, we get an array of arrays, because each time this is happening, it's continuously doing this. So it's always passing like, perform the prediction, load the result into an array that's being that stores these arrays. And then we find the maximum indices of the first element in each array because the most prominent element or the most prominent motion will pop up the most in the first element. And then we pass it off to create an emotion array, which it's just simply like happy, sad, neutral. And then we use the maximum index to select each one. And then we display the emotion on the screen. So this is happening continuously. And then when we hit Q, we save the image and then we quit out of the program. Do you want to do this, Abraham, or you want me to do it?
I'll do it.
Okay.
Can't read that, but basically, this is like a program that we use, and this is the program that we use to implement our emotional detector. So we had to start off by downloading Anaconda Navigator, and we had to install certain libraries such as Dumpy, Keras, Pandas, NCV, etc. So basically, these are all imagery libraries that required for the emotional detector, and I just lost the screen. Hold on.
You good?
All right, but yeah, I lost the screen for a second. And wait, can you zoom in on it? I can't read it.
Okay. So once we install it, you create the folder where the directory is going to be at, and if you wanted to load it onto like say a secondary hard drive like D or E, you can just type in the letter and the colon, and it'll change it to that directory. And then once you load it up, once you load up the terminal, and you load up everything in there, then you type in Spider to open it up in Python, and then you have to run train. We say train.python, but I forgot to update this. But once this creates the neural network that will be used to perform the predictions in the emotion detector. So without this cannot run, even though we call this the main program. And that's pretty much the whole like overall design view of our project. So to go into, do you want to do it?
Yeah. So once again, relating back to the last slides, these are all the tools that we had to use. Basically a webcam, Anaconda Navigator, a train database, Spider EDE, which was where we programmed OpenCV, Keras, TensorFlow, Pandas, Python language. So basically referring back to the last slide, that's what we used to implement for the motion detector.
So as you can, no, you can go.
So for implementation, we were able to implement the neural network for the prediction of the emotions. We were able to modify it, even though it was a challenge. And last but not least, we was able to find a way to save the pictures of the emotions to a directory. So the challenges was for me personally was basically coding, because I have least experience with that. But thanks to watching certain tutorials, doing research, I was able to create something little by little, by creating baby steps.
Yeah, I would say the same challenges. Like Python was not really a language that I do not really like understand too well, but once Abraham started linking me like the tutorials and stuff, I was able to start developing the sort of sense needed to produce the code bit by bit, little by little. I would say that the more difficult part was trying to find documentation on some of the functions that we use, because it was either really vague or just didn't really have too much. Like, it required us a lot of digging, and I would say a lot of time was spent just researching in general. And unfortunately, like, we weren't really able to figure out how to save the picture to a different location. So
Yeah, I would say another challenge is finding like the right program to use. Which like took most of our time. So,
yeah. So for the testing summary, there is a typo there. I should have said save image to database, not directory, because we were able to save it to the directory. So we were able to test the webcam to be able to capture the face, and it did. It was able to detect an emotional state, and multiple people, I had my brothers help me out on this one, and we were able to do that, even though they're not here right now, so I can't test that in the live video, but we were able to do that as well. The only thing we weren't really able to do is like create a separate database to hold the imagery to. And like I said, this is a typo, so. In terms of reflections, I would say this is probably one of the projects where I really bit off more than I can chew, because initially when we were writing this whole thing, it seemed very daunting in the sense of like we weren't really know where to go, or rather where to start. Like I said, Python wasn't really a language I used too much, so I had to look up like standard Python syntax and stuff all the time. And definitely time was another factor as well. It was definitely one of my more in terms of personal time, like I had a lot going on as well, so definitely wasn't making enough time for the project. We meet up whenever we could through Discord, which really helped out a lot, because all we did was just ping each other. But definitely, I did learn a whole lot, more than I should, about this whole project, because the amount of effort it took to really make this all together was really, really insane. That's all I could really say about this. And I kind of wish I wrote down more in the design notebook about this as well, like learning about all these programs, learning about like the environment, how to make something work. I would say it was time well spent, even though, you know, most of my personal time was just being eaten up, but it was still time well spent.
on my end, well, first overall, even though we were able to get the motion detectors done, but we did have certain more things, such as adding detecting ages through the image. Leave if you could classify hair color, which personal research I did to try to be more creative with the project, but for our minimum experience, and I'm very happy in little time that we were able to do something and able to show something to with our least experience. So I definitely did learn a lot about coding, especially with this new library that I researched in Content Navigator, because the main reason, well, one of the main reasons why I was open to do this project, because I thought about how certain apps such as like Snapchat, Instagram stories were developed. So with my least experience, you know, I felt like this was a good opportunity to learn certain things from the background how it goes. So maybe one day, if I decide to create an app, you know, I could definitely rely on what I did this semester and like build off of what I learned. I really wished we had a little bit more time, like I said, to add more features to it, but definitely with this little time, as Anthony said, I wish I could have write more as well. Notebook, but I did write a decent amount of things that I felt like was good enough for me to remember. Definitely um, use this project, for future projects that I would like to do in my career or in my life. So yeah, pretty much it for me.
Any questions?
Anthony, I'll ask one. What's
Okay.
the motivation for this project? So I think it's very interesting. If we were in the classroom, I'm gonna walk to your camera and test it. So like the motivation, where it can be used, the context. I know like these days, many places use the facial recognition.
Yeah.
So just that kind of, can you just elaborate what motivated you to do this project?
So personally, I'll answer this question. Like I said, beginning of this project, I thought about certain apps such as that first. Secretly, I did want to do a music and motion detector, but I felt like with my minimum experience, I won't be able to do all that. So I wanted to keep it basic. So, like I said, I thought about Snapchat and how everybody nowadays use their cell phones with Snapchat. So the motive for me was, and Anthony, I believe as well, was to start off with an emotional detector to see how it goes, and maybe sometime in life we could try to um, put more features and try to create an app one day, of our own. So that was like the motive I had in the back of my head to create this project and take advantage to learn.
And I would say like my motivation to making this would be just to try something out that I really haven't where I really haven't like really explored in terms of technology. Like I always thought about like other things as well, like quantum computing, stuff like that. But then when I did a bit of research into like this re-detecting emotions through like a webcam and how like relatively like how really complex it could really make out to be, I knew that this was probably going to be the project that I wanted to work on. Even though I couldn't spend too much time on this, it was definitely something that I really enjoyed working on from top to bottom.
Thank you.
Yeah, thank you. All right, thank you so much.
Yes.
Good job.
Thank you.
Good job, guys.
Oh, sorry, my bad.
Yeah, nice job. It was interesting how the project started out, focusing on a music playlist kind of creator based on somebody's emotion, and I think the research they did will still be able to head down that. They got all the hard stuff. So, good job. Next up, secure file transfer. Joseph, please.
Braverman, I just have one request. I have to go to work. I didn't realize this was gonna take that long. I can do my PowerPoint, but could you just play the video and at the end?
Yes, sure.
Like, can you see the full PowerPoint?
It's playing it in the presentation. It's fine.
I don't know how to get
So my name's Joe Montano. I did secure data transfer as my project. So the way I started off, started researching jobs and what interested me, and I wanted to go into cybersecurity or somewhere in the IT field. So with that information, I was looking at jobs in terms of analysts, like cyber analysts, or um, like data transfer, any type of data analysis position. So after that, created a problem statement. Mine was about how a company can securely transfer data, whether it be remotely, more so remotely. So if you have people who have to work from home and they need to log into their computer, access all the work files and so on. So from there, create a high-level problem, then defined how I was going to make and implement the solution for this problem by creating high-level diagrams and specification sheets, and explain basically what kind of system I will make. My problem statement: a company has a problem with its secure data transfer. Create a successful way to secure data transmission from user to cloud. So my first thought was for remote access. Basically, what I just said before, having the user be able to remote in from work and make sure that no information is exposed to outside users or any type of people trying to hack into the network. From there, I went to my development process. So I started with a architect design for the project, schematics, not schematics, but just like a diagram of what I think of how I would solve it. Then from there, element diagrams and implementations, as well as like system specifications, so what the system's going to need. Then created a preliminary design layout with models and flowcharts. Then started to create a more detailed layout of everything and explaining how those functions would work with my system. And then implemented everything, and I used VirtualBox as my test base, basically. From there, my requirements and requirements analysis and traceability. So the system shall be able to handle large amounts of traffic on the network with no latency delays. That's a big one. Second one, the system shall have easy accessibility to like new updates, patches, easy interface. And the system shall provide all transmitted data. Make sure that like all transmitted data has integrity, confidentiality, and is authentic. And I said it should use SSL protocols as one of the protocols it should use. My system architect. So my subsystem, basically making a test environment. So I use VirtualBox. It was a lot easier to use VirtualBox than create a system out of hardware. And so basically I have my first VirtualBox. This would be my home computer, and then inside my home computer I have my virtual machine, which I then had 2 host machines on it, which would connect to the internet. Then would connect to, once the VPN was connected, connect to a VPN, which would connect to the VPN server, and then the data would be transmitted from there to the data server, and then back to my host machine. This was the interface for VirtualBox that I used. Designs and models. So I wasn't really, I was creating a test environment, not creating something from like scratch. So it was more of like a data analysis. So the left picture would be one of the commands that I used, which was the ping command. And basically you're talking from one machine to the other machine with an echo request. So it's sending an echo request from the host machine, goes through the network, goes through switch, the router, then it goes after the router, hits the goes to the VPN, then through the encryption of the VPN, which is the tunnel, hits the VPN server, then from the VPN server to the main server, back all the way through back to your host machine. So with that ping, you want to have a low ping for low latency. Otherwise, when you're trying to connect remotely, you're gonna have a lot of issues. It's gonna be slow, and it's not gonna be workable. The next one was for integrity of the data. So a checksum. Basically, a checksum checks the data being sent. So when a packet's sent over the network, it gives it a number. The numbers have to match from sender to receiver, and for order the packet to be transmitted securely, which is what shows in here. So the sender gets a bit, and it goes through. After it goes through the transmission, then they compute to make sure it has that bit, and then if they have the same one, they accept it. If it doesn't, it rejects it. So the packet gets dropped. If packets get dropped, it means it can mean two things: either you're losing information to somebody, or it's dropping off in the VPN. So for my implementation and details and tools, so I used Wireshark also to capture packets. I used VirtualBox for my test machine, and then the 3 VPNs I looked at were CyberGhost, Hotspot Shield, Surfshark, and Command Line. I chose these 3 because I can get free trials for all 3 of them for their premium service for 2 weeks, so I was able to not have to buy anything and just use the free premium VPN service just for my testing purposes. And then the command line. So I use the command line to use my ping commands, and yeah. So my results. Here, I'll just bring it up here. So I did. I looked at latency, the integrity and confidentiality / authentication of the data. So for CyberGhost, it has 7-second millisecond response time. When I pinged I used Google as my destination server. I pinged and it got 7 milliseconds. My upload and download was 70 megs down and 240 up. Then I pinged, sending 200 packets that were, each packet was 100 bytes, response time of 12 milliseconds per packet. That showed basically that if the VPN was under load, a high traffic load, to see what the response time is and if it could handle it. I used, for the integrity of the checksum, I looked through Wireshark and looked at all the packets that were displayed as I was capturing them, after I captured them, and see if there was any transmission errors. CyberGhost had 1 transmission error. Again, that could be from, I was not 100%, it's 50-50, it could be from either the packet being dropped or from what I researched, it could just be a fault. CyberGhost also uses ESP protocols, which is shows integrity. Then for Surface Shark, it was a 9 millisecond response with 64 megs down, 335 up. I did the same test with the pinging, and it was a little bit slower at 15 millisecond response time. For the integrity, I did Wireshark and looked to see if there was any errors. It had 8 retransmission errors, which was a lot more than CyberGhost did. And then the final one was Hotspot Shield. That was the fastest response time at 1.8 milliseconds. And it had 260 megs down and a little bit slower of an upload at 135. But response time with 200 packets at 100 bytes each was 4 seconds. So it was the fastest. And then for confidentiality and authentication, I used an IP torrent to check to see what my IP was when the VPN was running, and if it was not, if when the VPN was running, it was a hidden address basically, which wasn't my home address. I concluded that it had authentication, and all of them, when all 3 of the VPNs were on, all the data all the IP addresses were different than what my home IP is. But in conclusion, I thought CyberGhost was the best, even though it had a little bit slower response time than HotShield. It had less retransmission errors, and it uses a encryption protocol for encrypting the data. So I think that was, in my opinion, the best from what I researched. And then reflection, overall, things that didn't go so well. Time, I work 50 hours a week, so to be able to put a lot of time to this while also taking 21 credits was a little challenging. Also working independently, when you get stuck on something, it's kind of hard when you're sitting there for like 2 hours looking at the screen thinking about the same thing and don't have anyone to bounce ideas off of. It's a little frustrating. I could have written scripts instead of just using the command line, like write a script and then output everything. Didn't have the time. And I also wanted to change up the configurations in the VPN. You can change either using UDP and TCP. There's another one you can use, I don't remember the name. And testing all those, but again, didn't have time. Overall, I think I learned a lot more information about VPNs than what I've previously knew about them, and I learned a lot about the different protocols and encryptions that are used and how they're implemented. And that's it. Any questions? And then. Thank you.
Joe, did you say CyberGhost uses an encryption protocol and that's different than the other VPNs?
It uses one of them that was displayed. It uses ESP.
Familiar with that one?
They all have some. They all have some type of encryption. Yeah, it uses encapsulating security payload. But just like looking at Wireshark, you could see the ESP packets. Like it has header for them.
It's like easily recognizable as ESP, you're saying?
Right, it was easy recognizable in Wireshark versus the other ones didn't have anything that I noticed right off the bat.
Did the other ones use TLS at least to encrypt the...
Okay. They did. Alright.
Any questions for Joe before we let him go to work, apparently?
I gotta go to work.
I didn't know you worked at night, Joe. I would had you go early.
That's okay. Yeah, I work night third shift, so.
Any questions for Joe? We'll play your video, Joe.
Okay.
Stick around as long as... Okay.
senior design project. Secure data transfer. I created a virtual box, rather a virtual machine, to allow me to test different VPNs. I picked 3 to look at. CyberGhost 8, Hot Shield, and Surfshark. So first one, CyberGhost. If you look at it, my goal was to imitate if you were trying to connect as a remote user to a company. So my tests were to try to reflect as if I was connecting to a company and server. So first, like looking at this VPN, looks easy. Quick connect button. Start. It's connected. You can see it's using the IKEV2 protocol. This one shows your download and upload speeds and your new IP address. Now, for my first test, I used Wireshark. From there, I implement or act as if I was going to go to my destination server, which in this case is Google. Then looking at the traffic, you can see they use a lot of TPC protocols. There is, where is it? There's a couple transmission errors, retransmission errors, which I was looking at for integrity of the data. The retransmission error is when the checksum is looking through the data, it's not validating it, so that packet that was sent was not validated by the end receiver and was not confirmed by the sender, so the packet was dropped. That's what the retransmission error is. So there's a couple, quite a few actually, for this VPN. Now, I don't know if that's 100% due to the VPN, or it could be another issue. But this shows that this VPN has some integrity problems. Other than that, now I went to my next test, which I ran a speed test, and I did a latency test, so I used the command line, and I was looking at ping Google, and so an overall response time of 14 milliseconds, minimum, maximum, average about 14, but no packets were lost during transmission. Taking that, I tried to implement as if you were going to be using heavy traffic over the network to make sure that the network doesn't get slowed down. So with that, I would use the ping command, and then you can put the packet size. So I was going to do 10 packets at 100 bytes each, and I'm going to ping Google. Unfortunately, the command's not working, but
yeah, I mean that's
when it
something
was,
I wonder whether
there was a response time. I was sending
having somebody who's not qualified to be.
My other test scenario that I did was 200 packets at 100 bytes per packet, and I got a response time of about 12 milliseconds, which is still pretty good. Then comparing this to another VPN, same process. disconnect from this one. I'm gonna look at Surfshark. Connect to this one. This one is also an very easy interface for someone to use. You can come over here to settings. If you come down to connectivity, a lot of different options in auto connect. So if you are working at home and you're on a laptop and the administrator could have this enabled, so you never have to worry about connecting the VPN manually every single time, which is nice. Some of the other features is not features. Some of the other settings. So you can also change the same protocols, but this one has a shadow socks. I'm not sure what that is, but then they still have the normal TCP, UDP, and WireGuard. Now this one's connected. You can go to Wireshark. Start a new recording. And stop. 6. Here, go to Google. And then stop this. And this one also you can see, in terms of integrity of the data, there's a lot of retransmission errors. So, there is data packets being lost. Some of the data is, again, doesn't have integrity, but for the most part, everything looks confidential. You can also go into statistics. You can look at the your packet, each packet, the packet lengths. You can look at how many packets in total, and then the percent and the burst rate of the packets. And so yeah, with this information, I had some more tests. I can't explain it all in the video, but overall, looking at the 3 different VPNs I just showed you too. In terms of latency, the fastest VPN was HotShield. Had the fastest upload and download speeds by far, with 260 megs down and 135 megs up, and had a response time of 1.8 milliseconds. In terms of integrity, the VPN that had the most integrity was CyberGhost. It had the least transmission errors. That's what I was using. And also, I was also using the ESP protocol. You can see that in the Wireshark. And for confidentiality and authentication, I used IP torrent to check IPs. So, looking at the IP address, if my IP address was visible, if I could search, if it showed my home IP address and not a different IP address, I would know that it's the VPN doesn't have authentication. It's not using the tunneling protocol. It's not working. It's not working how it's supposed to. So yeah, out of all, I would choose CyberGhost to be my company's VPN. Thank you.
Okay, hopefully you can hear me.
Yeah, we can hear you.
Okay, thanks. So Joe's is gone, I believe, but this video, those are all the presentations. Good job to everybody. Don't forget to submit your final, or make your final Bitbucket rating and submit your RTT, OneDrive, and all your submittals in Blackboard. Okay. So thanks to all the visitors or spectators, and thanks to all the great job.
Good job, everyone.
Thank you for the class. I hope you have a nice day.
Bye, everyone.
Thank you guys.
Presentation.
Bye.
Thank you.
Oh, Braverman. Me and Javier submitted our PDFs. In the comments, I left the link to our Bitbuckets. Is that enough?